In this video we're going to look at binary to decimal conversion, also known as denary, and later we'll look at decimal to binary, also known as denary to binary conversion. So the most important thing to remember with binary numbers is what the digits are worth. So the first column is always the units, then the 2s, 4s, 8s, 16s, 32s, etc. Every time we move to the left. It's a multiplication by 2 because it's base 2. So if we take a number as an example, the binary number 1010, and we can tell it's binary because we're going to put a 2 there. If we didn't have that 2, we'd assume it was decimal or denary, and that would be 1010. But in binary, it's not worth that much. So always start from the right, I would advise, so that you put your digits in the right place. So 0, 1, 0, 1. So we're going to work out what that is equal to in base 10. Well, we're multiplying and we're adding effectively, although it doesn't look as though we are. That's what we're doing. So we have one lot of 8, and we have no 4s, so we don't bother adding that. We have 1, 2. So 1 times 2 is 2, and we add it to the 1 times 8. So that is worth 10 in base 10. So that's a simple example. We'll do another. So I'm going to take 1, 0, 1, 0, 1, 1, base 2. And what's that worth in base 10? Well, again, you could put it into a table, or you could just write what each column is worth above it. Units, 2s, 4s, 8s, 16s, and 32s. So this number, we have one lot of 32. And we also have an 8. We also have a 2. And we have a 1. So look for number bonds. 8 and 2 is 10, plus 32 is 42, plus 1 is 43. So let's check that answer using the Windows calculator in programmer mode. So if I click on binary and put 101011, it shows that the decimal or denary answer is 43. So we know we've got it correct. Do another example. Let's take 1111 001, and I would advise to set them out nice and neatly, normally with like equal spacing, especially when the numbers get longer. So just to show that, I'm going to write that more spaced out. 1, 1, 1, 1, 0, 0, 1. Otherwise you're going to end up putting things in the wrong place. And that's our units, 2s, 4s, 8s, 16s, 32s, and 64s. So we're going to multiply and add. So one lot of 64 is 64, so that's a base 2 number, remember. This is a base 10 number. We also have, so we're adding one lot of 32. We also have a 16. We also have an 8. There's no 4s and no 2s, but we also have 1. So again, 32 and 8 makes 40, plus 64 is 104, plus 16 is 120, plus 1 is 121, base 10. So let's check that with our calculator. You can click on decimal or denary, and we can put in 121, and in binary it is 1111001, which should be 1111001 is what we had. The calculator shows a leading 0 because it does it in groups of 4 bits, as like computers work. They do 4, 8, 16, 32 and 64-bit architectures, so we don't worry about leading zeros because they're not worth anything. So no matter how long the binary number is, all you need to do is write the units and the 2s, 4s, 8s, 16s, etc. Then wherever there's a 1, you add one of that number. When there's a 0, you don't add it. So hopefully that'll be quite straightforward. Write some down yourselves and have a go. I almost forgot, you'll be feeling shortchanged, that I said that in this video we'll be doing decimal to binary conversion as well. So let's have a look at that. Let's pick a random decimal ordinary number. 100, we can tell it's decimal, so we put base 10 there. So how do we convert that into binary? Well, as usual, we need to have our binary place columns. Units, 2s, 4s, 8s, 16s, 32s, 64s, 128s. But the number that we're starting off with is less than 128, so we could never put a 1 in there, because one lot of 128 is bigger than 100, so we don't need this column. And the opposite of what we did earlier, multiplying and add, effectively what we're doing is dividing and subtracting to get our answer. So we ask ourselves, one way of seeing it is 100 divided by 64 gives us 1 and a remainder. So really what we're doing, we're saying 100 divided by the 64 column equals 1 point something. So we know that we have one lot of 64 and 100, and we know we have a remainder. So 64 fits into 100 once, and then we subtract. We say, well, what's left over? So we had 100, we've now accounted for 64 of it. So technically here what we're saying is 100 take away 64 equals the remainder, which equals here 36. So 36 is our new number that we need to represent. And what we're technically doing then is saying, what's our remainder? 36 divided by 32. And that's going to be 1 point something. But an easier way to see it is to say, well, what's 36 made up of? It's bigger than 32, so we know there must be a 1 in there. And then we say 36 take away 32 is 4. And how do we represent 4? Well, we can't put a 1 in the 16s column because we only have 4 left as a remainder. So we put a 1 in the 4s column, and now we've completely finished. And put zeros in every other column down to the units, otherwise the number will look smaller. So let's see if this is correct. So using our calculator, we want to have, click on decimal, put 100, and in binary it's 1100100. 1100100, so that is correct. And of course, if you wanted to do the inverse operation to work out if it is correct, you can say, well, one lot of 64 plus one lot of 32, which is 96 plus the 4 equals 100. So we know we've done it right. So we'll do the next example a little more quickly, a little more straightforward. I just had to show the processes that we were doing. So 300 in base 10 is equal to what in base 2? Well, again, units, 2s, 4s, 8s, 16s, 32s, 64s, 128s, 256s and 512s column. We know we don't need the 512s column because 300 is less than that, so we wouldn't be allowed to put a 1 here. So we don't need that one. But 256 goes into 300 once with a remainder of 44. So how do we now represent our remainder? 44. We couldn't put a 1 there because 64 is bigger than 44. I'll just make a quick note so we don't forget what we're doing. 300, take away what we've represented already is 44. So that has to be a 0 because it's bigger than 44. That has to be a 0. But 32 fits into 44 once. So now we've got 44 remainder minus 32, which we've accounted for is 12. And 12 is made up of 8 and 4. The rest have to be put as zeros. So let's check our answer. Press all clear, click on decimal, press 300, and the binary number is 1 and then 2 zeros, then 1 and a 0, which is right so far, then 2 1s and 2 zeros, so we've done this correctly. And finally I'll do one more. $1,020 in base 10 is equal to what in base 2? Slightly longer number, so I'm going to start off over here. Units, 2s, you know the routine by now. Double check the columns. We haven't missed any out. So 1020, we couldn't put a 1 there because 1024 is bigger, so we don't need this column. But 512 fits into 1020, and then we do the remainder. So we could write 1020, take away 512, that's equal to 508. 508, well 256 fits into that. So we have 508 to take away 256. You could do it in your head or you could use a calculator and that'll give you an answer of 252, which is our new remainder. 252, 128 goes into that. So then you just keep subtracting the number that you've just accounted for. The next remainder is 124. 64 goes into 124. So we take away 64 from that remainder, which leaves us with 60. 32 goes into 60, so take away 32 from 60 gives us 28. 16 goes into 28, so take away 16 from 28 gives us 12, and 12 is made up of 8 and 4. So quite a long number, so the answer is 1, 1, 1, 1. It's good to group them into 4s. 1, 1, 1, 1. 0, 0. So technically speaking, we should group them into 4s from the right hand side. So really, I should have written 1, 1, and then another group of 4 1s, then 1, 1, 0, 0. And if we check that on our calculator, let's do it in binary mode for a change. Click on binary, I put 1, 1, then 4 more 1s, then 2 1s and 2 zeros. In decimal tells us that's 1020. So we've got it right. Happy days. I hope you found this video useful, so try some yourselves.